Yeah, thank you for inviting me. It's really nice to have this talk. So let me just begin. The talk is on looking at the night sky in the very high energy range. I'll explain more about how we talk about very high energy. Just to begin, to give a brief, this is how we started looking at the night sky. Probably the first time it was just cavemen looking at the stars, and sometime in between in the medieval era, we started to look outside the sky ceiling that we had, and finally we have somehow gotten through this stage where we can uh, analyze in various energy ranges using different techniques. And you may be familiar with this picture of a black hole that we had observed a few years ago. And uh, we had simultaneous observations from various different telescopes. So I'll explain a bit more later, but not on this particular image. But in general, we have come this far by just trying to observe the night sky. And to understand the different messengers that we have, that we use to detect or see in the astronomy field, we have the standard old electromagnetic spectrum, where you can see from radio to gamma rays, depending on the wavelength, frequency, or the energy scale. And to just show in comparison what sources emit those radiations, you have some images over here, and we can only see in this visible energy range. The In the talk for today, I'll mostly concentrate on the energy range over here, around more than 1 GeV, or 1 giga electron volt. To talk about another messenger, they are the energetic particles, be it the electron positron pairs, protons, or what we like to call cosmic rays, or even neutrinos. So this is basically the energy flux, depending on the energy range that they are in. So you can see that there is a definite spectrum pattern where it follows a certain power law index, as I can say, uh, but only at certain ranges. If we combine all of them together, it's not really clear right now as to how it should be, but we are still investigating. As it can be seen that we have detected energies of particles about few EEVs, or what was earlier called the oh my god particle. And this is in comparison with LHC, how much, at what energy can they observe. So this is basically comparing the observations made by various telescopes, detectors, and instruments. And finally, the new member of the multi-messenger astronomy is the gravitational waves. And they are, you can see the various sources and the types of detectors that we have and wish to have, or we can theoretically have. And they, here you can see the frequency range. So this is the other end of the spectrum of what we normally use in the electromagnetic spectrum. So all of these combine to form the multi-messenger astronomy. And this is the new advent of modern astronomy. But I will concentrate today mostly on this energy range, and mostly talk about the electromagnetic part of this astronomy. To give outlook of how many detectors or instruments or telescopes we have based on this high energy or the new astronomy. Here are the ones in circles are the ones that are active and operational, and in triangles the ones which are planned for the future. So as you can see, we have a lot in the northern hemisphere and some in the southern as well. Here I have combined gravitational waves as well, because most of the processes that lead to gravitational waves that can be detected by us are the ones which are caused by extreme physics, extreme phenomena in the universe. So we can talk about some counter processes or emissions in the electromagnetic spectrum, or by some neutrinos, cosmic rays, or something like that. So there's a bigger synergy in these three astronomies. So this is just to show the outlook. Now let's go into this very high energy realm. So just to show that in general, we define high energy astronomy to be including X-rays, gamma-ray astronomy, and also neutrinos and cosmic rays. This is because we talk about high energy as something which is a few keVs, kilo electron volts, and above. In this growth term, there is no upper limit in the energy scale, but to be more specific, we define very high energy range to be around 100 GeV to around 10 TeV, or maybe up to even 100 TeV. And well, this is one classic example of how we compare this energy scales with classical objects, like the flying mosquitoes. Kinetic energy is around 1 TeV, and you can imagine how it scales to particles and subatomic particles having the same energy. So in astronomy, in this energy range, it's mostly dominated by gamma and cosmic rays coming from the extrasolar sources, that is not from within our solar system. We do observe, we do get gamma rays or cosmic rays in this sense from the sun, but in the general sense of astronomy, we would concentrate more on the extrasolar sources and move ahead with that. To just clarify, cosmic rays are it's basically a misnomer. It was how we started calling them, but they are mostly relativistically charged particles with non-zero rest mass, or rather to say that they are not light particles or waves. And they were first discovered by Victor Hess in 1912. And at that time, it was thought that they come from somewhere in the cosmic region. So that's why the name was termed, and we basically never bothered to correct it or change it. So cosmic rays are now in general term for the relativistically charged particles. And we can observe them either by direct detection or indirect detection methods. I will not get into too much about the direct detection method over here because that's beyond the scope. But just to show about the different knowledge bases that we require to study this field of astronomy, and mainly from the STEM fields. So many of you would know quite a lot of them or some of them. So just to classify them in physics, mathematics, and engineering and technology. So I'm assuming that you have studied at least the classical mechanics, electromagnetism, some form of thermodynamics. But beyond this, we also talk about the dynamics aspect of these physics. We also need to know about statistical mechanics and definitely the relativities. Both of them are very important in this astronomy. A general idea of astronomy and astrophysics is very essential. But also quite important is to know quantum mechanics and at least an introduction to quantum field theory, because we deal with such energetic processes and phenomena that we need to understand how they happen. And well, this is the realm of quantum physics. For mathematics, some basic trigonometry, differential and integral calculus, some tensor algebra. Now we get more advanced with differential geometry, conics, statistics and probability, very important in any data analysis in physics. Group theory, this is more of a territory for general relativity and quantum field theory, and some other advanced algebras that one might need. It's not my idea to list everything, but just to give an idea. And in the engineering technology section, we need to know certain computational languages. We need to have some basic or advanced programming expertise. For astronomy, you basically need some knowledge about photonics. It can be advanced or some basic level as well. And definitely we have to understand how to maintain the telescope or observatory or the detector that we are working with. So there is a significant need of people with such knowledge base. And obviously that we work with large data servers and data storages, so we need to understand how they work and how we can operate with them. So next, I'll just talk about some gamma ray sources and themes one can find in this link over here about this image. We broadly define them in two categories. Is one to study the non-thermal universe, where one can talk about sources in the galaxy, like the stellar binary, supernova remnants, etc., or outside our galaxy, like active galactic nuclei, gamma-ray bursts, etc. One can see some small images over here, and this is basically how many high energy sources that this new upcoming CTA consortium or the observatory will observe, and the range of observation that we have. And just to highlight that, well, the galactic sources we need to we'll see around the galactic plane itself. That's one clear area to look at. The other aspect of or the theme is to study some fundamental physics. This is not really dependent on the source that we observe, but with the aspect of trying to find the evidence or some physics or something like that. So one prominent of them is doing some indirect dark matter searches. Unfortunately, or for whatever reason, we still have not found any dark matter particle or to understand them either by direct or indirect methods. But in gamma ray field, we can use indirect methods to try to find such or some candidates for dark matter. We can also have some possible exotic effects in this gamma ray propagation, like Lorentz invariance violation, action-like particles, etc. I'll go through them one by one in the next slides. But just to give you the other context is that in general, we want to find the origin of cosmic rays. They are in general from such big accelerators or high energy environments which can produce such high energy particles. One of them is obviously a black hole or a supermassive black hole, and well, they are really a great candidate to study, and X-ray astronomy, radio astronomy, and various other fields of astronomy also look at these objects. But gamma ray astronomy provides a rather fitting end in the spectrum of the analysis of such objects, because we are only interested in the particles that are coming with relativistic speeds. And the other is obviously doing some dark matter searches. Now, next, sorry for the quick one. What we in general try to observe is Crab Nebula, or which is a standard candle in gamma ray astronomy. It's basically a supernova remnant, which happened, the supernova happened in 1054 AD. It was an observable and widely observed phenomenon. People could see it in the daylight as well. And as one can see in these images from different electromagnetic wavelengths, from radio to gamma rays, how they differ. So one can clearly infer from this that we will definitely study some different physics or different aspects of physics by observing in different wavelengths. And it's, as one can see from this gamma ray source image, that it's a very steady and very bright, or the brightest source that we can observe in our sky. And therefore, it's our standard candle for doing any gamma ray astronomy. So whenever somebody wants to observe anything, one definitely needs to check whether you can observe the source properly. If not, well, then you have something wrong happening. And also because it's like a point source, not diffuse or wide like the other aspects in these images. It's a very quick and easier performance check for any detection method. If one can just overlay all these images, except for the gamma ray part over here, one can see that we have a pulsar at the center of this supernova remnant, which we also call the Crab Nebula, Crab pulsar. And one can see there are some jets. One can see in X-ray more clearly about the jets phenomena, and also probably infer from radio. But here is the image of a model of the pulsar that we think it is. And how we detect is by observing them, the fluxes or the number of events that we can. And basically a pulsar is a rotating neutron star. So if the jet is facing us, we will get a spike in the events. And if it's facing the other way, we have a smaller spike as well. So in this way, we can make a phasogram or do some phase analysis of the source, which is a really good way to find or to study pulsars. And it can be used in various other astronomies as well, because the pulsars have a very timely spin phenomena. So it's very easy to use that as a standard for some different astronomical searches. So this with Crab Nebula, we go to define some more broader aspects like the galactic sources. So we definitely want to observe, or we can observe, the galactic plane. Here you can see from the Fermi lat observation of this night sky, this is the galactic plane. This is observed in 1 GeV energy range, and we can see that there is a clear, significant spectrum over here. So it's a really good source for observing. And it will contain some stellar binaries, some supernova remnants, like we observed with Crab, or pulsar wind nebula. These are just different types of sources that we can observe. And just to give uh, more observations. This is one with a pulsar and a BE type star, or something with a microquasar, where we have a compact object which is a black hole with maybe jets. So that's there, and the other is with when the companion star is a very massive star. So all these variations will have different effects, different emissions, different ways of studying them or analyzing them. So depending on the light that we receive from the sources, we can infer of how they are processing, how they are moving around, how much, how much the jet is moving ahead, or the stellar matter is being sucked in by the compact object, or something like that. So we have a lot of physics to study, and one can see from here the example is these are mostly from electron and proton-proton interactions, and whereas in these sources it's from electron and photon interactions. So we do classify based on the particle reactions that we have or that we can observe from the sources. The next aspect is the extragalactic sources. On the right side, you have the unified model of active galactic nuclei. That is a galactic center which has an active black hole. Generally, it's a supermassive black hole, and one can see various aspects of black hole that can have, and depending on what we observe or not observe, or how we observe, we will classify those objects relatively like that. So suppose you see it from this side, from this angle, we'll say it's a Cepheid 1 galaxy. If we see from this side, we'll say it's Cepheid type 2. If we also define based on the radio emissions, whether it's loud or quiet, whether we see the jet directly in a line of sight, we call it a blazar. If we see some aspect from this side, we can observe some phenomena from maybe the torus around the black hole, which is basically the region which has a lot of gas, a lot of stars surrounding the black hole. And basically over here in this tunnel jet, you have a lot of energetic particles that are thrown out. And one of the sources of gamma ray production is the jet. The others can be other regions of this. So once we try to compare more astronomical data, we have a broader understanding of the HEN. The other source is called gamma ray burst. So here you can see central engine, as we like to call it, or it's mostly a black hole or a supermassive black hole, or it can also be merging neutron stars, or any phenomena which will result in a burst of energetic jets of particles. And this is based on fluid dynamics, based on statistical physics, on the relativistic acceleration of particles. So here the particles move at some speed, they get accelerated, and further down the line, you have light in the gamma ray region, and at a much later stage, they fizzle out or they lose some energy based because of some absorptions. So you have some afterglow. So this phase can be observed at lower energy scales in X-rays or some other energy bands as well. So what we in gamma ray astronomy are concerned with is the region over here. And this phenomena happens within few seconds. This is the scale of this burst is few light years, at least. So you can imagine how quickly, how fast this phenomena happens, and it's a rare sight. And we did some recent observations of such GRPs, and because of the nature of this engine, depending on the type of central engine they have, we can observe different physics and analyze more data based on that. And it's difficult to observe GRB in gamma ray energy band. It could be based on our position in the sky, in the universe, or just our luck. But recently we have some, so it's a good avenue to look into. The other is the dark matter indirect search. So, well, dark matter searches are one of the hot topics in physics. We still have not figured out what they are, how they behave, how they interact with other particles, and the composition is still a very well contested topic. In this scenario, that the dark matter is comprised of weakly interacting massive particles, which is one of the leading theories of the component of dark matter. And if the mass is within the range of some GV to TeV, the annihilation or decay of such dark matter particles may produce gamma rays, which can be detected by gamma ray telescopes. And here you can see that depending on the different energy masses of such WIMPs, there is a spectrum in different energies from this is 0.1 GeV to a few hundred TeVs. But we are still not here yet that we can observe from our current sources, current telescopes. And this is the Fermi, the space-based telescope, and these are all the ground-based telescopes. CTA will be a much better improvement, but still, well, we'll hope that if this model is not correct, then there might be some other theoretical prediction that might help in understanding or analyzing dark matter particles. So this is a very open area of research, and because we do not have anything direct, so what we usually do is provide some upper limits or some limits in the flux that we can observe that could be dark matter. So this is a very statistical, it's a big statistical problem of when we have a non-detection, as we like to call it, or what we want to expect when we have a much more improved telescope or detector. But well, that's for the future to see if we get lucky or we are not. The final aspect is if we want to go beyond standard model physics. This is more exotic nature, as it can be said. Well, because we are working at such high energies and we are looking at astrophysical regions of extreme environments, one can look for some theoretically predicted phenomena and try to see if we can find any evidence to support such theories. One of them is something called actions, which is a proposed solution to the strong charge parity symmetry violation problem of quantum chromodynamics. And I'll explain a bit what's a charge parity violation is that uh, charge symmetry is when you have particles and their anti-particles, rather with opposite charges. And the idea is that if a phenomena is happening, if a reaction or interaction is happening with one charged particle with whatever set of particles, it will be the same if a particle with the opposite charge and with a symmetric position, parity meaning better spatial position. So if both of them are reversed, then the phenomena will be the same, or it will have the same energy, or it will behave similarly. Well, this is the idea of symmetry in the quantum field of quantum chromodynamics, which mostly deals with strong nuclear forces. So we still do not have a solution why such symmetry breaks. But a proposed solution is that there can be some intermediary particles called actions. So these are one of the various theories and predictions of quantum chromodynamics, and it can also be simultaneously be part of the cold dark matter, or it can be the whole dark matter. So it's still one of the aspects where various different beyond standard model physics groups work with. So for our use case, such action-like particles, they could decay into photons or vice versa, like photons interact and create such action-like particles. Uh, and that could come in the range of gamma ray observations based on the energy scale of the proposed action-like particles. So far, we have not observed. So, well, the search goes on. The other more fun aspect of beyond standard model physics is to try to find evidence of Lorentz invariance violation, uh, which might be associated with quantum gravity effects on space-time at the Planck scale. Now, this is more related with how special relativity defines Lorentz invariance principle, and that all moving objects in an inertial frame will be the same even if you change the frame of reference. So uh, we think that there is a limit of this invariance principle, that at higher energy scales or at the Planck scale of energies, this principle will be broken. Uh, that's one way of looking at it. The other way is if we try to talk about quantum gravities, it has been suggested that such effects, quantum gravity effects, may induce time delays between photons with different energies, but traveling over large distances. So when they interact, there's a time delay between these two photons or more photons, which will correspond to some non-trivial refractive index of the vacuum. So with this time delay, if we can observe such delays from expected spectrum, like for example, the AGNs, that we know how they behave, how their spectrum should look. And if we find that there is some uh, disparity in the timing interval or the incoming photons time from the expected spectrum or from the spectrum that everybody has analyzed and observed, then it can be the evidence of such Lorentz invariance violation. And well, we might have to update our physics, update the standard model physics, and we might have to uh, uh, accept quantum gravity as that theory suggests. But again, we have not found any such violations, and we just actively look for it. So this is one phenomena that is connected to gamma ray astronomy because the scales at which we think such violations can happen are the scales between different galaxies. So when we are analyzing AGNs or GRPs, this is one active component that we look for. And we also compare it with various other phenomena that happens like the extra background light or some effects from various magnetic fields, either within our galaxy or galaxies or between galaxies or various other fields like the cosmic microwave background. So those are the known physics, known phenomena. So we compare with such effects and see if there's something that cannot be defined by the standard model physics. So we always compare of how much we know, how much we can analyze, how much we can deduce from the spectrum that we get. So, well, this is one of the hot topics of finding more exotic physics using gamma ray astronomy. Now I'll just move on with how we make some observations and something about the statistics. So why it would be difficult to observe or make such observations is because the Earth's atmosphere, the incoming high energetic particles will get absorbed and cannot reach the surface. This is a big problem even for X-ray telescopes. And so that's why we have space telescopes. So for gamma ray astronomy, we have like Fermi, which have the benefit of having unfiltered data, but they also have various constraints like size of the detector, the maintenance facilities, the cost of putting such a space-based telescopes, etc. They also have a constraint of the calorimeter technology that they use for observation, which has a limitation of observation above 100 GeV. So if you want to observe more energetic photons, we need something better. So we do try something like ground-based telescopes, which work on indirect detection, unlike space telescopes. So we use something called the principle of Cherenkov radiation, which is caused by various particle interactions of relativistically charged particles in the atmosphere. So I'll explain briefly on how this radiation works. So this was discovered by Soviet physicist Pavel Cherenkov in 1934. So the basic idea is that this radiation is emitted whenever a charged particle traverses a medium at a speed larger than that of light in that medium. So you can imagine that this is the medium, this is the emitted particle that we have, and because it's charged and it's moving, so it will attract, it will polarize or make dipoles of the neighboring particles, molecules, etc. Now, this is normal when the velocity is not relativistic with respect to that medium. So this refractive index value is important over here. It depends on the medium. But when the velocity is higher than the speed of light in that medium, that is this, we see something like this happening, that the particle moves faster than the light can move. And one can see that it's more of a geometric way of looking at things, like how the particle will move. So this radiation results from this reorientation of electric dipoles in that medium. And with that, what happens is that we get some sort of blue light, which is called Cherenkov radiation. So this radiation is observed from ground-based telescopes and using different methods to make an inference that this phenomena happened because some high energetic particles did come across the atmosphere and produced this radiation. So one aspect is having extensive air showers. On the left side, there's a GIF on how a shower looks, and this blue radiation is the Cherenkov radiation. So these are mainly produced by two processes. It can be either electromagnetic in nature or hadronics, or hadronic, which is basically produced by hadrons like protons, neutrons, nucleons, etc. So electromagnetic, basically either by pair production or Bremsstrahlung radiation, and hadronics are when the cosmic rays particles, remember we talked about it, having relativistically charged particles with non-zero rest mass. So when they interact with the atomic nuclei in the atmosphere, they break into charge and neutral pions. And then these pions, they further decay into either muons and neutrinos, or also produce their own electromagnetic showers. So as you can see in this animation, there's a shower of such particle interactions. And when they happen, because of the primary particle having very large energy over here, they produce Cherenkov radiation. Now it matters how and where we observe this phenomena, this Cherenkov radiation. If this radiation is observed in the atmosphere, we call the detectors as imaging atmospheric Cherenkov telescopes like MAGIC, HESS, etc. Whereas if this is observed in a water container, a large water container, we call them as water Cherenkov telescopes. They are like Hawk, Lasso, etc. So for such water Cherenkov telescopes, you basically need a large amount of water containers. This is almost similar to how neutrino telescopes work, but with that, you can have a large area of detection, whereas when you have IACTs, you can see over here, these are example of two. These are the two MAGIC telescopes. Obviously, this is an artistic rendition, not exactly this location, but it's to see how they operate and how they look like. So we cannot simply build a lot of them just like that. But what we have now is the upcoming CTA telescope array, which will be something like we'll have around 70 or 100 telescopes, both in combined in northern and southern hemisphere, as we could see from the earlier map and their locations. And they would be basically be the largest array of such ICTs. Now, to just talk about how we analyze the data, it's very brief. I'm not going into the details of it, but because of the nature of such high energetic physical interactions, we have Poisson distributions of such incoming signals. So we define such statistics and we work with them. We also have a large number of background events, so that we have to clean them, calibrate our signals to get the correct signal from the primary particle or from the primary shower particle. And this results in having low statistics at higher energies because of all the atmospheric absorptions. And so we have to invest heavily to get as many photon counts as we can, so we can properly analyze the data in any significant manner, uh, which will be more relevant when we are observing it more than 10 TeV or 100 TeV scales. So there you get very few charged particles, because if you could see, maybe I can just show briefly, go back. Yes, over here. So you see that this spectrum falls down with high energy. So if we, even if we see the GeV to TeV scale that we are, the charged particle, which would be normally cosmic ray proton, the flux falls very quickly, which means that the number of charged particles that we can observe falls as quickly as this. And therefore, we have, at higher energies, we have to be very specific about the statistics that we use to analyze such data. And yeah, we also investigate some correlations between fluxes observed from various electromagnetic wavelengths or the other astronomies to say something significant about the sources that we saw earlier, so that we can have a better understanding of the physics that happens, because uh, it's not just one phenomena uh, producing energy in one energy range. Everything works together, so we have to have some combined analysis, and we all work together based on that. Now, just to have talk about the day today of the International Women's Day, just wanted to say some a few words on why we need more women in this field. This is just my opinion as not a sociologist, but as somebody who is working over here in this field, and that women in general are more organized and methodological and have been generally brought up like so, which is very essential when we are analyzing anything in astronomy, and even more when we have such low statistics, such low data, and we need better optimized data analysis. Now, this field of astronomy owes a lot to the dedicated efforts of various women. Uh, I didn't have time to go through everyone. It would probably take another hour or so to just mention that. But it's a very well documented fact that it's the case. And because it's a very interdisciplinary and innovative nature of this field, it requires various diverse viewpoints to converge together so that we can make a quick and correct physics based on the observations. And well, basically, women just need to reclaim their space and lead this field. So that's just my take on this. As a man, I cannot say more on this, but let's hope it comes true. Well, that's all from my side. Thank you. So probably now we can take some questions if there are. Mhm. Mhm.